Welcome to Lab 4, Magnetic Field of a Bar Magnet. In this lab, we'll go through an intro, visual models, the experiment and results, as well as the coding, and finally the discussion. So the goal of the lab was to observe the distance dependence of the magnetic field from a bar magnet by measuring that magnetic field on-axis and off-axis using Biot-Savart's law. Then we modeled a magnetic field in Python and compared experimental results to the model. And a quick preview of the results was that the net magnetic field increases as distance decreases, and our magnetic dipole moment was found to be 83.7 amps times meter squared. And a quick note about the off-axis data. My lab group was not able to complete the off-axis data during our time, so we have an external resource who will be mentioned later. So going into Biot-Savart's law, this describes the relationship between the magnetic field produced by an object and the current of that object, as well as the distance between the object and the observation location. We have several different equations for the magnetic field of various different macro versus micro perspectives of a current carrying loop or wire. The magnitude of the magnetic field perpendicular to the magnetic dipole moment is half the magnitude of the magnetic field on axis to the magnetic dipole moment. And the magnitude of a magnetic field due to a bar magnet can be represented by the following equation, where K is a combination of magnetic constants. And then we also have a general formula for the magnetic field of a magnetic dipole. And in our visual model, we know that the system is the observation point, which in this case is our magnetometer, and our surroundings are the bar magnet and the Earth and any other sources of magnetic fields. For our experiment, we had a bar magnet, meter stick, magnetometer app, and a device to access Excel. So we first oriented the phone such that the X component was 0 to compensate for the Earth's magnetic field. Then we located the magnetometer chip, and we measured the on-axis magnetic field as well as the off-axis magnetic field. Now again, as I mentioned earlier, our lab was unable to complete the off-axis magnetic field measurements, so we do have other data from an outside source. Here is our data collected in lab with our graph, and this is sourced data credited to Siobhan. For our analysis, we have that the equation of the regression line, where n is the slope and the y-intercept is the natural log of k. In order to find the corrected magnetic field in the y direction, we subtracted the magnitude of the Earth's magnetic field in the y direction from the measured y component of the magnetic field at the off-axis observation location. We noticed that when the magnetometer was far from the bar magnet, there was a near zero value measured in the x direction, and if the magnetometer was placed closer to the bar magnet, the measured x component of that magnetic field increased. Over here we have our constants, as well as the function to calculate our magnetic field, and we use the general formula for the magnetic field of a magnetic dipole. Over on this section, we have the scaling part of our arrows. And over here on the following page, we have the rest of the code for our arrows, which includes the location of the arrows as well as what they represent. And over on this side, we have the calculation of the off-axis magnetic field with the corresponding magnetic field arrow. And the following is our output. Over here, we have our values for the magnetic dipole moment, our experimental magnetic field off-axis, and the modeled off-axis magnetic field. Again, these off-axis values were assessed via the outside source. So there is a 172% difference between our modeled and experimental values. Some possible sources of error include other sources of magnetic fields, an inconsistent alignment of the phone, surface inconsistency, as well as measurement errors when recording distance between the magnetometer and the magnet. So as the distance between the magnetometer and the bar magnet decreased, the magnitude of the magnetic field increased. If we hadn't oriented our experiment to compensate for magnetic north, the x and y components would have increased because of the contribution from the Earth's magnetic field to both of these components at an intermediate angle. The z component of the measured magnetic field would not change because the magnetic field would continue to be measured from a flat surface, so the z component, again, would remain constant. If we were to stick two identical magnets together end to end, the measured magnetic field would increase to reflect the magnetic field of both magnets added together. This means that we would see the magnitude double that of one magnet. And the measured distances would decrease to reflect the increase in the magnetic